Continuing on in Chapter 6, types of intermolecular forces. We've kind of hinted at these. We were talking about things evaporating and melting, and we talked about forces that were holding the particles together, and how in order for something to evaporate, it had to break through the red rover line. And sometimes it's kindergartners in the line, and sometimes it's COS linebackers in the line. And how fast you have to run at them to get through the line would vary depending on how strong their grip is in that line. So intermolecular forces are like the grip between the people in the red rover line, how strong these particles are attracted to each other. Intermolecular, that prefix inter, means between. Intermolecular, between molecules. This is different than the ionic bonds and the covalent bonds that are within a molecule. These are between individual molecules. The strength of these intermolecular forces is going to determine the state of a substance at room temperature. If there are strong intermolecular forces, then those substances are going to be liquids and solids. If the intermolecular forces are weak, it will be a gas. We've studied gases, and we understand that under many conditions, gases act completely independently of each other. They do not interact with the other gas particles. And that's a weak intermolecular force, very low interaction. There's three kinds of intermolecular forces. So the first one we're going to talk about is the weakest one. And it's your book uses the term dispersion force. It's also called London forces. Some books call them London dispersion forces. When I was in school, we called them van der Waals forces. That's worse, isn't it? That's a crazy Dutch name. And they are also sometimes called induced dipole forces, which is actually my favorite name for them because it's more descriptive. But that's not what your book uses. So all of these names refer to the same kind of a force. So I'm going to try to call them dispersion forces. Dispersion forces are caused by fluctuations in the electron distribution within molecules or atoms. And because all atoms and molecules have electrons, all substances have dispersion forces. So that's important to understand. All substances have these dispersion forces, regardless of what kind of a atom or molecule they are. So what happens is that the electrons in an atom or a molecule could at any given instant be unevenly distributed. Okay, we talked about electrons, and at the very least I hope we learned that they're squirrely and unpredictable, right? They are not orbiting the nucleus in nice circular orbits like the planets go around the sun. It's nice to think of them that way, but that's not what they're doing. So at the very least, we can say they're very squirrely. So let's look at these illustrations of a helium atom. Here we've got the nucleus, and helium has 2 electrons. So here's a picture of helium at one time, and here's a picture of helium at another time. You see that the electrons are just in there somewhere, right? And here's at a third time. Now this time, both of the electrons just happen to be on one side of the atom. That's going to cause the electron distribution to be lopsided. All the positive charge is on the nucleus. All the negative charge is on the electrons. If the electrons are not evenly distributed around the nucleus, then we get one part of the atom being a little bit positive and one part being a little negative. And it just happens randomly. So I've told you many times I have 6 kids, right? And usually when they're all home, they are not all in the same place. They spread out. The house is relatively big. Sometimes we wish it was bigger. But there's places they can get away from each other, and they often do. They move around, but usually they're kind of spread out. I have a picture. I think this has probably only happened once. Spontaneously, they all ended up on the same half of the couch. 6 kids piled up on half the couch. I don't remember why. I got a picture and then the moment was gone, and it'll probably never happen again. It can happen though. Electrons are a lot like children. They're kind of unpredictable, right? And so here we've got these two electrons, and usually they're kind of away from each other, spread around, but occasionally they might be closer together, just randomly. Okay? This causes what's known as an instantaneous dipole, or a temporary dipole. Remember, a dipole is when there are two poles, two ends that are different. Right here we have a dipole. We have a negative and a positive. It's not an ion, but there's a separation of charge. All the negative charge is here, the positive charge is there. So there's a separation. A temporary dipole. Great, so what does that do? Well, a temporary dipole in one helium atom can cause or induce a temporary dipole in a neighboring helium atom. Because if this helium atom is close to this one, here's this positive charge. That positive charge is attractive to the electrons. And those electrons are going to be drawn to it. Oh, hey, look, we like that. And they'll go over to the side. It's a little bit like a blue and white cruise boat in the San Francisco Bay. And there's, lots of people on deck, because the reason you're on the boat is so that you can see, right? And you're going out around and you get close to Alcatraz. And maybe Alcatraz is on the left side of the boat. The people on the right side of the boat, I can never remember starboard and port. The people on the right side of the boat, are they just going to hang out there and not see Alcatraz? No, they're drawn to Alcatraz, right? They go around, they hear the other people, hey, look at that. And they go around to the other side of the boat. And that causes the boat to tip just a teeny tiny bit. If it was a little boat, we'd be in trouble, but it's a big boat. But you get all the people on one side, it tips just a little bit. So this boat is a little tipped, and that attracts tippingness in the next one and in the next one, and this can go on and on and on. When we have a temporary dipole in one atom and a temporary dipole in the next atom, now we've got a force of attraction between these two. And then this guy goes back to being random, and it all goes away. So it comes and goes and comes and goes very, very quickly. And so it's a very, very weak force, but it is significant. So we've got this instantaneous dipole on one helium atom induces an instantaneous dipole on a neighboring atom, and then those atoms are attracted to each other. That's why I like the name induced dipoles, because I think it's descriptive. Dispersion, I don't like that word, but there it is. That's what we're calling it. So the dispersion force occurs as neighboring atoms attract one another. This instantaneous random dipole induces a dipole in a neighboring atom, and then they're attracted to each other. These are transient, meaning they don't last very long. They come and go. Oops, wrong pointing place. They are transient, constantly appearing and disappearing. So they're very weak. A covalent bond is always there. Covalent bonds are very strong compared to dispersion forces. The magnitude of the dispersion force depends on how easily the electrons in the atom or molecule can polarize in response to an instantaneous dipole. And this is going to depend on the size of the electron cloud. If you have a large electron cloud, it's more easily polarized. So you've got a big crowd of electrons and an instantaneous dipole. They will more easily form another instantaneous dipole. I gave the example of children at Disneyland. So now my older two are in college, so they're fairly responsible, but think back a few years. If I went to Disneyland by myself with 6 children, that would not be a good idea, but let's just say I did. Am I going to be able to keep track of all those children all the time? Am I always going to know where every single one of them is? No way. You can't watch 6 moving things at one time. So large family, easily polarized. They could all be on this side or that side, who knows? Think of a mom going with one child. Is she going to know where that one child is? Yes. Small family, small atom, less easily polarized. So I don't know if that'll help you remember it. So the molar mass reflects the size of the electron cloud. It alone does not determine the magnitude of the dispersion force, but we can use it to help us compare similar things. So let's look at the noble gases. Helium, neon, argon, krypton, xenon. They are all in group 8A in the periodic table. They all have full valence shells. They're all monatomic atoms in their natural state. So they have a lot of things in common. And if we look here at their molar masses, we see, as expected, we're going down the periodic table, the molar mass is increasing quite significantly. Xenon has a molar mass of 131. Here's helium with a molar mass of 4. Okay, helium's tiny. Xenon's pretty big. And then we can look at their boiling points. The boiling point is a measure of the strength of the intermolecular forces. Because in order for that substance to boil, the particles have to have enough energy that when they get to the surface, they can break through and break free from the forces that are holding them together. If those forces are weak, like they are for helium, helium atoms have enough energy at 4 Kelvin, which is like minus 269 degrees Celsius, really, really, really cold. They have enough energy at 4 Kelvin to boil. As we go down here, the size of the atom increases, larger atoms are more easily polarized, the strength of those dispersion forces increases, and the boiling point goes up. For xenon, you have to heat those molecules up a little more to 165 Kelvin before it will boil. Still really cold, but 165 is significantly larger than 4. Do you see the idea there? A higher boiling point tells us that the forces holding that substance together are stronger. So let's look at these two, CH4 and C2H6. Which one do we expect to have the higher boiling point? Let's first notice that these compounds are similar. They both have just carbon and hydrogen. What's different about them? Are their molar masses going to be different? Yeah, because CH4, carbon's 12, hydrogen's 4, so that one's about 16. So that has a molar mass of about 16. And this one, 2 times 6 is 12. Wait, no. 2 times 12 is 42, plus 6 is 48. So that has a molar mass of 48. This has more atoms, and so we also expect it to be larger based on that. These molecules only experience dispersion forces. Which one's going to have stronger dispersion forces? The bigger one, right? So the C2H6 is going to have a higher boiling point. We can't say anything about what the boiling point is, but we can look at two compounds that are similar, and we can predict which has the higher boiling point or which has the higher melting point. The second type of intermolecular force is called a dipole-dipole force. And this one doesn't have lots of different names. It's just, I've always referred to it as dipole-dipole force. This exists in all polar molecules. Dispersion forces are found in everything. Dipole-dipole forces are found in polar molecules. What's different about polar molecules? Well, they don't have temporary dipoles, they have permanent dipoles. Right? We've talked about what a polar molecule is. So the dipole-dipole force, like in its name, dipole-dipole, it's a force of attraction between two dipoles. So it's the attraction between the positive end of one dipole, the negative end of another. All molecules have dispersion forces. Polar molecules also have dipole-dipole forces. So this results in polar molecules having higher melting and boiling points relative to nonpolar molecules of similar size. If the molar masses are the same or similar, the strength of the dispersion force is going to be the same. But a polar molecule also has dipole-dipole forces on top of that. So this is formaldehyde. Here's its structure. And if we look at that structure, do we expect that to be polar? We've got a slide coming up about this, but what did we learn about how to predict whether something's polar or not? We should look for lone pairs on the central atom. Are there any? No, because here's carbon. It's got 1, 2, 3, 4 bonds. It's got its octet, so it's not going to have any lone pairs. And then we look to see, is everything bonded to the central atom the same? No, we've got an oxygen and we've got 2 hydrogens. And so what we find when we look at the space-filling model is this is lopsided, isn't it? Here we have hydrogen on this side and water on that side. They have different electronegativities, so we end up with a polar molecule. This end is slightly negative. This end is slightly positive. So we get an attraction between the positive end of one and the negative end of the other. This isn't something that comes and goes because that dipole is always there. It's a permanent dipole. It's a polar molecule. And so we always have this force of attraction. So the dipole-dipole forces are going to be stronger than the dispersion forces that come and go. Here we can look at formaldehyde. That's the molecule we were just looking at. Here's its structure again. We see that it's polar. And ethane, and that's one we looked at in the previous example. Here's the structure of ethane. And we look at that and this is so nice and symmetrical, isn't it? You can't really say, well, this end's different than that end. On this one, this side is different than this side. This is a nonpolar molecule. Their molar masses are almost identical. But look at their boiling points and melting points. Minus 19, minus 88. That's pretty different. Minus 92, minus 172. Why does this boil at a higher temperature than this one? The molar masses tell us that the dispersion forces are roughly the same, but this one's polar and it also has those dipole-dipole forces. Stronger intermolecular forces, higher melting point, higher boiling point. And we see that the melting point is also higher because of the dispersion forces. Dipole-dipole force also affects miscibility. It's a word I don't think we've used in this class before. So miscible sounds a lot like mixable, right? Mixable isn't, I don't think that's really a word, but helps us to remember what miscible means. Miscible is a term we use to describe the interaction between two liquids, where a liquid can mix with another liquid without separating into phases. So they're mixable. Polar liquids are generally miscible or mixable with other polar liquids, but they are immiscible, not miscible, with nonpolar liquids. So polar and polar will mix together, nonpolar and nonpolar will mix together, but when you get opposites, they're not going to mix, polar and nonpolar. And we see this when we have oily hands or oily stains on clothes. Oil is nonpolar. It's a liquid, but it's nonpolar. Water is polar, and it just doesn't do any good washing that oil away. Here we have an illustration of pentane. Pentane has the formula C5H12. Just carbons and hydrogens. It's a very nonpolar substance. And so here it is. It's going to sit at the top, and here's the water. Because the nonpolar substance doesn't interact with the polar substance, and so they don't mix together. Here we've got oil and vinegar. I have that exact cruet at home. Don't know exactly where it is, but I've got one just like that. Here we've got the oil and the vinegar. They're not going to mix. Oil is nonpolar. The vinegar dissolved in water is polar. They don't mix. Oil spill. oil in whatever kind of form, if it's crude oil or whatever, it's nonpolar and it doesn't mix with the seawater. So all polar molecules have dipole-dipole forces, and we need to be able to identify whether a molecule is polar or not. So the book's method is determine whether the molecule contains polar bonds, and then determine whether the polar bonds add together to form a net dipole moment. Is that a valid method? Absolutely. That's the best method. Does that make sense to most students? No. And that's why I came up with Mrs. K's method, which works most of the time. It doesn't work all the time, but you know what? Most of the time is pretty good, especially in this class. So, and I've covered this before, so we're just reviewing here. A molecule is nonpolar if both of these conditions are true. No lone pairs in the central atom, the atoms bonded to the central atom are identical, or they have the same electronegativity. And most of the time, just identical will be good enough. So let's determine whether or not each molecule has dipole-dipole forces. This first one, that's Ci4, not Cl4. That's why I put the name here, carbon tetraiodide. Well, we need to look at the structure. We really should look at the Lewis structure. So there's a carbon in the middle, and there's 4 iodine atoms bonded to it. Now, those iodine atoms are going to have lone pairs, and if you want to go ahead and figure all that out, that's great. But we actually don't have to go that far. We can just look at the central atom with the 4 bonds that we know from the formula and ask ourselves, does that carbon have an octet of electrons? Yes, it does. From the bonds, because each bond is 2, and it counts for both of them. So because it has 4 bonds, the carbon has an octet of electrons. That tells us there's no lone pairs. So that's the first condition, no lone pairs. That one's true. The second condition, are all of these atoms bonded to the central atom identical? Yes, they are. So that means that this is a symmetrical molecule, and even if the carbon iodide bonds are polar, it doesn't matter because they all add up and cancel each other out. So this is a nonpolar molecule. Does it have dipole-dipole forces? What kind of molecules have dipole-dipole forces? Polar molecules. So this is a no. It doesn't have. What kind of forces does it have? The first one. Remember its name? Dispersion forces. So this is nonpolar. It's going to have dispersion forces, but not dipole-dipole forces. CH3Cl. Well, the C is in the middle. We've got H's, 3 of them, and Cl. Polar or nonpolar? Polar. Why? This one's different. They're not all the same. It's like that Sesame Street. One of these things is not like the others. One of these things just doesn't belong. Okay, it's this one. That one's different. That's all the farther we have to go. This is polar. Do polar molecules have dipole-dipole forces? Yes. So this one is a yes. How about this guy, HCl? This is 2 atoms. How do we tell if that's polar? Are the atoms different? H and Cl are different, right? So odds are very good that that's going to be polar. So then yes, this does. Remember, there are a few elements in the periodic table that have the same electronegativities as each other. But most of the time we can assume that if the elements are different, that the bond is polar. So we're not going to get hung up in little details for this. We're looking for big picture ideas.
So basically, if it
Well, with this one, there isn't a central atom, right? There's no central atom. And yes, chlorine does have lone pairs, but there's no central atom. It's just two. And so if the bond is polar, the molecule's polar. Because we could have something else like hydrogen, H2. Is that one polar? No, there's only the one bond, and because these two atoms are the same, those electrons must be shared equally. Over here, regardless of these lone pairs, chlorine is more electronegative than hydrogen, and so the electrons are not shared equally. So one end of the bond is negative and one end is positive. Any other questions? The last type of intermolecular force is hydrogen bonding. And this occurs in polar molecules that contain hydrogen atoms bonded directly to fluorine, oxygen, or nitrogen. And these are called hydrogen bonds. I think the best way to think of them is that they are sort of a super dipole-dipole force. Dipole-dipole force on steroids. Okay, big dipole-dipole force, just extra big. Okay, it's the same idea of attractions between permanent dipoles, but it's extra strong. It's extra strong because the electronegativity difference between hydrogen and fluorine, oxygen, or nitrogen is extra large. These are the three most electronegative elements. And size plays into this as well. These atoms are small, which allows neighboring molecules to get close to each other. The strength of these forces, they are electrostatic forces, but electrostatic forces depend very much like magnetic forces do. They depend. They behave. So think about putting a magnet on your refrigerator. It sticks, right? Because you have a magnetic force. And then you use the magnet to put up a piece of paper. Still, it's good. And then you put up 2 pieces of paper, and 3, and 4. Depending on how strong your magnet is, you're going to come to a point very quickly where you have enough pieces of paper that the magnet isn't going to stick anymore. Is the thickness of, say, 10 pieces of paper, is that a very large distance? No, it's pretty small. You know, it's kind of hard to even guess it with your fingers like this. There's just a little tiny difference. That much difference, that much distance between the magnet and the refrigerator can be enough to cause the magnet not to stick. It depends on the distance. In fact, it depends on the square of the distance. So small change in distance, huge change in the strength of the attraction. Well, that's true for these electrostatic attractions as well, between positive and negative charges. When they get a little far apart, the strength of that interaction falls off. And so that's why it's important that these molecules are small, because then they can get really close together. So how do we remember when we can have hydrogen bonding? Did you guys see the movie E.T.? You know, I think it came out before you guys were even born. It's fine. It's a great movie, isn't it? What did E.T. say when he pointed to the sky? E.T. phone home, right? Phone home. Fluorine, oxygen, nitrogen bonded to hydrogen. If you've got ET in your molecule, you've got hydrogen bonding. Okay? It's got to be one of these. You have to have a fluorine hydrogen bond, an oxygen hydrogen bond, or a nitrogen hydrogen bond. If you have one of those, you can have hydrogen bonding. So here's an example, hydrogen fluoride. Nice simple molecule. Can this have hydrogen bonding? Yeah. Here we have the F from phone bonded to the H from home. So we've got a hydrogen-fluorine bond. In fact, that's the only bond we have in this molecule. But this can do hydrogen bonding. This bond is especially polar because fluorine is very electronegative. And so it hogs the electrons more than any other atom does. So this one has a larger partial negative charge and a larger partial positive charge. Additionally, these molecules are small and they can get really close together. So the attraction between the fluorine of one molecule and the hydrogen of a different molecule is the hydrogen bond. It's not really a bond. Okay, and students sometimes get confused. They say, well, but that looks like a hydrogen bond. So that's a hydrogen-fluorine bond. That's a covalent bond between hydrogen and fluorine. The hydrogen bond is the attraction between the fluorine of one molecule and the hydrogen of a different molecule. It is an intermolecular force. Here's methanol. So here we've got carbon. It's got 1, 2, 3 hydrogens on it. And it's bonded to oxygen, and the oxygen is bonded to hydrogen. Can this molecule do hydrogen bonding? Yes, because we have hydrogen bonded to oxygen. So the O from phone and the H from home. So we have an OH bond. This is an especially polar bond. So that makes the dipole-dipole attraction between this hydrogen and that oxygen especially large. That's why I say it's like a super dipole-dipole force. It's just extra strong. So here we can compare methanol with ethane. We've looked at ethane before. There's its structure again. Molar mass of 30.1. Here's the structure of methanol. When we look at its structure, we see, oh yeah, there's the OH bond. And this molecule is polar. I guess if we had to pick a central atom, it would be this carbon. And we'd say, well, there's no lone pairs, but this oxygen-hydrogen business is different than the rest. This is a polar molecule. We've got this OH going on here. Molar masses are almost the same. That tells us the dispersion forces are pretty much the same. But look at the boiling points. Methanol boils at 64.7 degrees Celsius. Ethane boils at minus 88. That's a big difference. Why? Well, all ethane has, its little nonpolar self, all it has is dispersion forces. Dispersion forces are the weakest. Methanol has dispersion forces and dipole-dipole forces and hydrogen bonding. So it's got everything. So methanol molecules are more sticky together than ethane molecules are. And so it takes a lot more energy to get them to separate. Let's look at hydrogen bonding in water. So here we have little structural formulas for water. We've got oxygen and hydrogen. And it's in this bent shape because there are 2 lone pairs on here that we're not seeing. But water is a bent shape. And it's got hydrogen-oxygen bond here and a hydrogen-oxygen bond there. So water can do hydrogen bonding. So the hydrogen of one water molecule is attracted to the oxygen of another. And here we have the same idea shown with the space-filling models. This is a negative end. It's attracted to that positive end. The boiling point of water is 100 degrees Celsius, which is remarkably high for such a small molecule. Its molar mass is only 18. Remember, ethane had a molar mass of 30, and its boiling point was minus 88, and water's plus 100. And we'll see a little more about water. Hydrogen bonding is really, really important for a lot of things. One of the things hydrogen bonding is good for is keeping the 2 strands of your DNA together. You may know that DNA forms a double helix. There are 2 strands, and on each strand is a sequence of bases. These are the bases: thymine, adenine, cytosine, and guanine. And they react with each other, interact with each other through hydrogen bonding. So here we have an oxygen, and over here we have a nitrogen bonded to a hydrogen. This hydrogen can hydrogen bond with that oxygen. And we've got hydrogen bonding here and here. And so we get 3 hydrogen bonds between those 2 pairs, 2 hydrogen bonds between these 2 pairs. So not only does it hold the DNA strands together, but it causes them to be complementary, because you won't have a thymine matching up with a guanine, because they don't match. It's like pieces of a puzzle. They don't match up together. When you put them in the right pairing, they match up together, and it's almost like, something with a magnetic clasp, and it just goes click, 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 and it all clicks together. This is just a summary of the different types of intermolecular forces, and you should understand what's in this table. So 3 types of forces. Dispersion forces are the weakest. Dipole-dipole forces are moderate in strength. Hydrogen bonds are strong. 4 intermolecular forces. They are still very weak compared to covalent bonds. Hydrogen bonds are about, I'm trying to write with white. It doesn't work so good on white. 1/10 the strength of a covalent bond. So hydrogen bonds are strong intermolecular forces, but they're still very weak compared to the actual covalent bonds in a compound. Dispersion forces present in all atoms and molecules. Dipole-dipole forces only in polar molecules. Hydrogen bonding only in molecules, ET phone home. FON bonded directly to hydrogen. So let's look at these 2 compounds, HF and HCl. Which one has the higher boiling point? We have to think about intermolecular forces. Which one has the strongest intermolecular forces? The HF. The HF has a hydrogen-fluorine bond. It can do hydrogen bonding, right? HF. So that guy has hydrogen bonding, dipole-dipole forces, and dispersion forces. How about the HCl? Can it do hydrogen bonding? No. So what kind of forces does it have? It's got dispersion forces and dipole-dipole forces. This is polar. You've got 2 different atoms, hydrogen and chlorine. There's a polar bond, so the molecule's polar. But HF will have the higher boiling point because it has the stronger intermolecular forces.